There isn't just one type of black hole. There are actually several kinds, and they form in very different ways. So let's go through them one by one. First up, stellar black holes. This is the most common way black holes form, and it all starts with a massive star reaching the end of its life. Stellar black holes begin with massive stars. These are stars many times heavier than our sun. Because they're so big, they burn through their fuel very quickly. Eventually, the star runs out of fuel, and once that happens, there's nothing left pushing outward, so gravity starts crushing the star inward. Right before the collapse finishes, the star explodes in a supernova, one of the most powerful explosions in the entire universe. After the explosion, the leftover core keeps collapsing. If there's enough mass left, gravity compresses it into something incredibly dense. And just like that, you get a stellar black hole, a place where gravity becomes so strong, not even light can escape. Most stellar black holes contain somewhere between 3 and 100 times the mass of our sun. Huge, but actually the smallest type of black hole we'll talk about today. Many stellar black holes hide inside binary star systems. They slowly pull gas away from a nearby star, which spirals down into the black hole. This is what scientists think that process actually looks like: a swirling disk of superheated gas right before it disappears forever. Alright, next up, supermassive black holes. These are the absolute giants of the black hole world. And unlike stellar black holes, these monsters sit at the center of entire galaxies. Most large galaxies, including our own Milky Way, have a supermassive black hole sitting right in the middle. Everything in the galaxy slowly orbits around this central region. While stellar black holes might contain a few dozen suns worth of mass, supermassive black holes contain millions or even billions of suns. So yeah, slightly larger. Our own galaxy has one too. The Milky Way's central black hole is called Sagittarius A star. Astronomers have been studying it for decades. Scientists actually discovered it by watching stars orbit extremely fast around an invisible object. Only something incredibly massive could create gravity that strong. In 2019, astronomers captured the first ever image of a black hole. This one sits in a galaxy called M87, about 55 million light years away. When gas and dust fall toward these giant black holes, they form massive accretion disks. These disks can shine brighter than entire galaxies. Some supermassive black holes launch massive energy jets into space. These jets can stretch for thousands of light years, which is completely insane. And here's the weird part: even though they're unbelievably massive, the black hole itself is tiny compared to the whole galaxy. So supermassive black holes are the gravitational anchors of galaxies. But the next type we're about to look at is kind of the missing middle between the small ones and the giant ones. Alright, next up, intermediate mass black holes. And these ones are actually a bit mysterious, because for a long time, astronomers weren't even sure they existed at all. For decades, astronomers could see small black holes, and they could see giant supermassive ones. But the middle category was basically missing, which raised a big question. If stellar black holes are the small ones, and supermassive black holes are the giants, then logically there should be middle-sized black holes too. These are called intermediate mass black holes. These black holes are thought to contain somewhere between 100 and 100,000 times the mass of our sun, which puts them right between the other two categories. Scientists think these black holes might form inside dense star clusters, places where thousands of stars are packed very close together. Over time, smaller black holes could collide and merge, again and again, eventually building a larger intermediate mass black hole. Astronomers have now found several strong candidates, usually detected through powerful X-ray signals coming from star clusters. One famous example is called HLX-1. It's one of the best candidates astronomers have for an intermediate mass black hole. These black holes might actually be the building blocks of supermassive black holes. Over billions of years, they could grow into the monsters sitting at the centers of galaxies. So intermediate mass black holes might be the missing link connecting small black holes and the giant ones. And figuring them out could help explain how galaxies formed in the first place. Alright, now we get into something a little more theoretical. Primordial black holes. These aren't formed from stars at all. They may have formed right after the Big Bang. The universe was incredibly hot, dense, and chaotic. Everything was packed tightly together. In some areas, matter may have been slightly more concentrated than others. Tiny differences, but enough to matter. If those regions were dense enough, they could have collapsed directly into tiny black holes. No stars required. These primordial black holes could be extremely small. Some might be the mass of a mountain, compressed into something microscopic. Very small black holes would slowly lose energy through something called Hawking radiation. Basically, they can evaporate over time. The smaller the black hole, the faster it disappears. Some might have already completely evaporated. Some scientists think primordial black holes could even explain dark matter, the invisible stuff that makes up most of the universe. The catch? We still haven't confirmed they exist. So for now, they remain one of the biggest mysteries in cosmology. So unlike every other black hole we've talked about, primordial black holes wouldn't come from stars at all. They would be leftovers from the very beginning of the universe. Alright, now things get weird. Rotating black holes, also called Kerr black holes, because apparently a black hole wasn't strange enough already. Most black holes don't just sit there, they actually spin, and some of them spin incredibly fast. When a black hole spins, it doesn't just affect matter, it actually drags space-time itself along with it. This effect is called frame dragging. Anything that gets too close is forced to move along with the black hole's rotation. No choice. Around a rotating black hole is a strange region called the ergosphere. Here, space-time is being dragged so hard that nothing can stay still. And here's the crazy part. In theory, you could actually steal energy from a spinning black hole. This idea is called the Penrose process. You send something in and somehow get more energy back out. Physics gets a little wild here. In reality, rotating black holes would look like this, with space itself being twisted around them. And here's the key takeaway. Most black holes in the universe are probably rotating, because the stars that formed them were already spinning. So rotating black holes don't just pull things in, they actually twist reality itself, which somehow makes black holes even more ridiculous than they already were. Alright, now we get into something a bit more theoretical. Charged black holes. Yes, apparently black holes can have electric charge too. A charged black hole simply means it has an imbalance of electric charge, either more positive or more negative particles. In theory, this could happen if a black hole absorbs more particles of one type of charge than the other, so it ends up with a net charge. That charge would create an electric field around the black hole. So now it's not just gravity pulling things in, there's also electromagnetic force involved. So now you have two forces at play, gravity pulling things in and electric charge potentially pushing things away. But here's the problem. Space is full of particles with opposite charges, so a charged black hole would quickly pull in opposite charges and cancel itself out, which means over time it would become neutral again. So charged black holes probably don't stick around for long. In physics, this type is called a Reisner-Nordstrom black hole. Not the easiest name to remember, but very useful in theoretical models. So while charged black holes are possible in theory, we don't expect to see many of them in reality. So charged black holes are a cool idea, but in the real universe, they probably don't last very long. Alright, now we go from massive to ridiculously small, micro black holes. And when I say small, I mean really small. These black holes could be smaller than atoms. Yeah, smaller than the stuff that makes up atoms. In theory, micro black holes could form during extremely high energy collisions. When enough energy gets squeezed into a tiny space, gravity can briefly take over. Scientists have even wondered if machines like particle accelerators could create these tiny black holes. But even if they form, they wouldn't last long, like not even a second long. They would evaporate almost instantly through Hawking radiation, releasing energy in a quick burst. The smaller the black hole, the faster it disappears. And micro black holes are basically all evaporation, no lifespan. And just to clear this up, no, these wouldn't swallow the Earth. They disappear way too fast to do anything like that. So far, we haven't actually detected any micro black holes. They're still purely theoretical. So micro black holes take everything we know about black holes and shrink it down to an almost ridiculous scale. Next up, binary black holes, which is exactly what it sounds like. Two black holes stuck in orbit around each other. Instead of falling straight into each other, they actually orbit around a common center of gravity, kind of like a cosmic dance. But they don't stay stable forever. They slowly lose energy, which causes their orbit to shrink. As they move, they create something called gravitational waves, ripples in space-time itself traveling across the universe. As they get closer, they start spinning faster and faster, until things get very intense. Eventually, they collide and merge into a single, larger black hole. This collision releases a huge burst of gravitational waves, one of the most energetic events in the universe. In 2015, scientists detected these waves for the first time using LIGO, confirming that black hole mergers really do happen. So two black holes go in, one bigger black hole comes out. pretty efficient, honestly. Binary black holes show us that black holes aren't just isolated objects. They can interact, merge, and literally shake the fabric of space-time. And finally, we have rogue black holes. These are the loners. No galaxy center, no partner, just drifting through space. Most black holes stay in predictable places, but rogue black holes are completely on their own, moving silently through space. These black holes can be created during galaxy collisions, where gravitational chaos can literally kick a black hole out of its home. Once ejected, they just keep going, traveling through intergalactic space. The scary part, you wouldn't see one coming, because black holes don't emit light. The only way to detect them is by how they bend light. This effect is called gravitational lensing. As a rogue black hole passes through space, it can slightly distort the stars behind it, like a moving gravitational lens. Now, before you panic, the chances of one coming anywhere near Earth are extremely low. Space is just too big, so these black holes just drift, completely silent, through the darkness of space. So those are all the major types of black holes, from tiny theoretical ones, to galaxy-sized monsters, to invisible wanderers drifting through space. And somehow, we're still just getting started understanding them. If you found this interesting and want more videos like this, you can subscribe to the channel. I post new videos every week, and with your support, I can make them even more often. Thanks for watching. A long pause.